We're going to start talking now about memory, and this part of the lecture is about acquisition, storage, and retrieval, and a little bit about how information gets into memory. So just some terms to get familiar with as we go through this chapter's lecture is acquisition. Acquisition refers to the process of placing new information into long-term memory. So as you'll see, we'll start talking about something called working memory, where we hold information, and when information is there, we don't necessarily mean or refer to it as acquisition because it can easily be lost and it is often not kept. Next, there's storage, and this, just like the word implies, refers to memory that is currently in storage within the long-term memory system, and it sort of just remains there until such time as it is used again. Finally, there's retrieval, and this refers to the process of locating information in memory and then activating it for use, and that just means bringing it back to the forefront of our mind where we're able to now think about it or use that information for whatever the task at hand might be. So one of the original models that looked or examined memory was called the modal model, and it arose out of a whole bunch of different types of researchers all trying to figure out how the memory system worked. And it contained three primary pieces of information, or functions, or locations maybe is a better way of defining it. So first you had sensory memory, which is where information directly perceived, not even perceived yet, but so information is outside the world and our various sensory modalities are able to pick up this information and they encode it as electrical impulses, and that basically is just raw sensory information. And so sensory memory was supposedly able to store for a very brief amount of time that raw sensory input. And so this was ostensibly before any time of significant processing had actually happened in order to perceive this type of stimulus that we are currently in the process of perceiving. As information moved through sensory memory and is then now processed in some way, it would move into what is referred to as short-term memory. And you'll hear this still a lot in common language, but it isn't used so much anymore, which we'll talk about in the next slide. So short-term memory was where we held memory for, like it says, short periods of time. And this is often when we were trying to remember things quickly, like a telephone number or a postage zip code. And it could also be where we would hold information that we had brought back from long-term memory, which we'll talk about in a second. And this is just when you recall something from, say, your childhood or from 2 days ago. This is then information taken from your long-term memory and brought back into your short-term memory for it to be processed in some way. Now, according to the modal model, information had to pass through short-term memory in order for it to be encoded into long-term memory, and this was often done via what is referred to as maintenance or some type of rehearsal, in which basically this implies a constant repeating of whatever the item is that you're trying to remember. So if I'm trying to keep track of area 1 code 510, I could say to myself over and over, 510, 510, 510, so on and so forth, until that piece of information was encoded and I would no longer forget it. Of course, not all information that arrived at short-term memory was actually then encoded, and some of it could of course be lost. And that's what this little arrow here is representing of information is sensed, it moves through sensory perception, somewhere in here it is perceived, it is then stored in short-term memory, but then never makes it out of short-term memory and is thus lost, thus we are not able to remember it at some later date. For information that is able to pass through short-term memory, it moves into sort of this big box here, which is long-term memory. And long-term memory just refers to any of the various events that we tend to remember from any period over the course of our lives. The main point here is that even though it implies long-term memory need not be from our childhood or from 2 years ago. If you have something in long-term memory, it is something you're able to remember after not having thought about it for a little while, even if that little while is just several moments. We would still refer to that as memory that is, or memories that are in long-term memory storage. Finally, of course, the little arrow on the top that is for retrieval is just showing that memories can be brought from long-term memory back into short-term memory. Now, this was popular about 50, 60 years ago, and since then has been updated in what seem maybe like some subtle ways, but these have some pretty significant impacts in how we think about memory and how memories are operated on and how memory is encoded. The two primary differences are that sensory memory and any kind of neurological location that went with it is pretty much absent in current literature. It is not really thought to exist as a physical space, and while there is a remnant, you could say, of certain sensory perceptions, a lot of that is just thought to be residual activation as flowing from our various sensory organs into our brain itself, and not actually a separate stop along the way that is storing this type of information. Next, in at least these types of fields, even though in common language one still hears the term short-term memory a lot, in psychology and neuroscience, we pretty much no longer refer to short-term memory as short-term memory. We now talk about something called working memory, and it is thought to be functionally different, I guess location-wise different as well, than short-term memory itself. So talking a little bit more about working memory, so instead of just being a specific place or box you can imagine in which we keep certain types of memories that we're holding in this short-term memory area, it is thought more to be about what information or memories we are currently working on or processing in some way, and those are what occupy our working memory. And it is not really thought to be a place in the brain whereby we have this little unique neural cluster in which we somehow move information from other parts of the brain into this region and thus operate on them there, and then they're moved back or forgotten or fizzle out or something like this. We no longer think about working memory in this way. Rather, as different activation patterns exist across the brain, many of which are associated with certain types of operations and processes, we tend to look at working memory now as these types of brain states as opposed to some actual neurological or physical location within the brain itself that this information is being stored in. A few differences between long-term and working memories. So the first and probably most straightforward is that working memory tends to be quite limited in size. There's only so many things that you can keep track of at any one time. And anybody who's tried to remember a grocery list without writing it down knows the fundamental limits of how many single individual items we can remember at any given time. Even though as we move through this lecture set, you'll see that there's some pretty interesting tricks and skills you can learn that can drastically improve your performance. In contrast to this, long-term memory tends to be huge. You can remember unbelievable amounts of information. Not only just, for example, remembering all the various different types of concepts and facts that you could be learning throughout the course of this class, but also throughout your entire tenure at college. Not to mention the fact that you have memories for most likely the last, on average, 20 years of your lives. And this is really, well, quite a lot of information if you think about it. And while this is not necessarily the best analogy, you could think about how quickly you can fill up your smartphones with just taking arbitrary photographs in just the general days, and then think about the fact that your brain is able to capture not only visual information, but tactile, olfactory, and auditory information in line with those visual stimuli, and remember so many of those events for years and years, which is an unbelievable amount of information storage capacity that exists in long-term memory. Now, another difference between the two memory systems is how easy it is to move information into those memory systems. Now, moving information into working memory, or holding information in working memory to be more precise, is very easy. I could say something to you of remember the numbers 786, and you could just hold 786 in working memory, most likely by repeating 786 over and over and over, but you can see with just one statement, it was very easy to put that information into working memory. But now as we go on, chances are that set of numbers will slip away, and it is possible that you will remember that in the third, fourth slide of this lecture set, that I said 3 numbers. The only way for you to remember that beyond this lecture set is if you were to encode that into long-term memory. And the chances are it will be much fewer of you, or yes, much fewer, who will actually be able to remember that set. And this is the same as when we're operating on information. Like if you think about reading for this class, you can read this information, you're holding that information in your working memory as you move through the chapter, but by the end of the chapter, you probably don't have all of that information encoded into long-term memory, even though for a brief moment, almost all of it was held inside your working memory. And so this just goes to show that it's very easy to move information into working memory, but it's relatively difficult to get information into your long-term memory. On the same kind of note, it is very easy to access information in your working memory, and this is largely because it is the information you're actually thinking about right now, and so therefore it is easy to think about. But information being pulled out of long-term memory is a little bit trickier. While it is, in our subjective sense, maybe not necessarily the most difficult to remember some of our most cherished childhood memories, it can be sometimes difficult to remember certain things, and many of us have had the experience of, I know this, I just can't remember. And that is ultimately difficulty in pulling that information out of long-term memory. And we'll talk about some of the reasons why that is beyond any type of neurological deficit. For many of us, those average moments in life are just a completely normal part of having the brains that we have. Finally, the contents of working memory are very fragile, and this just means that they are easy to be replaced and are not very enduring. Anybody who is trying to remember a phone number by repeating the, how many are there, 10 digits over and over and over, can be easily thrown off by an evil friend who sits next to them and as they're reciting the numbers starts saying other numbers to them. Just hearing those additional numbers will oftentimes break the memories that are currently held within working memory. While if information is encoded into long-term memory, that trick no longer works because that memory can be referenced over and over and is not subject to easy change. So these are primarily the differences between the working memory system and the long-term memory system. So limits in size for working memory versus long-term memory, easy to get information into working memory as compared to long-term memory, very easy to access information in working memory as compared to long-term memory, and the contents of working memory are very fragile as compared to long-term memory. So since we talked about short-term memory and its idea of being a location as not really such a thing anymore, and working memory being a state of the brain, is it fair to still talk about 2 different memory systems if it is just working memory is currently whatever memories from long-term memory are being occupied? And well, there are some specific properties, well, as mentioned before, about the differences between working memory and long-term memory, which gives us the indication that perhaps these are different physiological systems. But also there are some interesting patterns that we see when people are actually asked or required to remember certain lists of things and to see how and where they start to make mistakes or perform well. Many of these studies, at least the earlier and most straightforward versions, are oftentimes referred to as free recall procedures or paradigms. And these require people learn a list of words or images or other such things, and they are oftentimes presented for about 1 second for every word, maybe sometimes longer if they're looking at images. And then as soon as this list is presented to them and is then finished, they're asked to repeat back however many of those words or images that they can remember seeing, and the order in which they repeat them back does not matter, at least what is what's told to the participants. The certain types of words that they do actually recall and where those were in the original list is actually of great interest to these researchers themselves, and thus allowing them this ability to have free recall allows us to see what words at different places of those lists people are more or less likely to remember. Now, it does turn out that people tend to remember the endmost parts and beginning most parts of lists far better than they do for those sets of words in the middle. Now, here in this graph, on the x-axis here is the serial position, or the position the words held within a list. So here is the first word, the fifth word, the 10th, 15th, and so on. Moving up the y-axis, we have the percent of correct words recalled. So here you can see that in this list of about 20 words, people had near 100% accuracy for the last few words. They had relatively low rates of accuracy, about 1 in 5 for words between the 5th and the 15th position, and then they did a little bit better for the words between the 1st and the 5th. And now this is just a general graph to show you how this looks. Oftentimes people will actually have near as good performance for the first few words as the last few words, even though there's almost always a slight benefit to the words at the very end of this list. Now, we'll talk about this more as we go through the last few slides, but the phenomena by which we tend to remember the last few words of a list or items of a list is referred to as a recency effect, meaning just the words that are most recent to us in time tend to be remembered better than words further away from us in time. Another one is called the primacy effect, and this refers to the benefit we gain from remembering the words at the beginning of a list. And primacy, just like it implies, is those words that start off the list. It could be items or images as well. So thinking about recency effects, now here, as mentioned previously, is the term used to define increased memory accuracy for items at the end of a list. And this phenomena is thought to be the direct result of our working memory system and not our long-term memory system, even if, hypothetically, you were to go on and code those words into your long-term memory. Now, here we're going to look at 3 different conditions on this graph, which we'll come to in a second, but there are 3 different conditions that are relevant here. The first is just a standard free recall paradigm in which they are shown a list of words, and then immediately afterwards they're asked to recall that list of words in any order that they would like. The middle condition, or the next condition over, which here I believe is the blue line the purple line with circles, is the free recall with a 30-second delay, and here they were presented with the list, and then before responding after the end of the list, there was a 30-second delay period in which they had to do nothing at all. They just sort of sat there, waited for 30 seconds, and then the experiment was like, okay, now tell me the words. Finally, there was a free recall condition in which they were again given 30 seconds between the end of the list and when they were required to present the words that they remembered, except this time it was filled with an activity that should hypothetically use up some of their working memory. And the most common way in which we do this is to give people an original starting number, say 210, and say count back by 4s or by 3s or by 7s or something like this. And so they would do that for about 3 seconds or 30 seconds in this case, and then be asked, okay, you can stop that now, and now tell me what words you remember. Now, if you think about this task of being able to count backwards from a certain number by some other number, this occupies our working memories because we're holding several different sets of information in mind currently in order to successfully finish this task. Moving into this graph, you see here on the x-axis again that this is the serial position of those words, right? First word is here, the second, third word, fourth, fifth, so on. And then the percentage of words correctly recalled is presented on the y-axis. So as we saw previously, in most rates, people are doing well at the beginning. That's what we had expected to see. Their performance then drops pretty significantly as you move away from that first position, and then sort of their memory stays largely the same. And now for the immediate recall, which is this red line with the squares, you see that they perform just as well as that original graph I showed you, where we see again a boost in the last few words that they remember when they're able to recall those words immediately after. Now, when there's a 30-second delay, but nothing is filling that delay, they perform just as well. And you can imagine yourself in this kind of situation. You've just ended that set of list, and in your mind freshly are those last few words, and you have 30 seconds to wait, And so chances are you just repeat those words to yourself over and over, and then when asked to remember them, you still have easy access because you maintain them in your working memory. You see a drop-off in performance as soon as that working memory has been filled with something else. You've ultimately replaced the words that you could repeat to yourself with this standard delay with counting backwards from a certain number by some other number, and then trying to keep track of what number you're on, what's like the next number, doing some operations, and all of this uses up our available resources for working memory. And you see that this differentially impacts our ability to recall words at the end of a list, while making no effect whatsoever on words at the beginning of a list, which we will talk about is actually related to long-term memory and not working memory. So here you can see it is possible to isolate memory performance as related to one memory system and not the other. So just a little bit of information quickly about encoding information into long-term memory. So the example I gave of when you were waiting for those 30 seconds and just repeating the words over and over, this is referred to as memory rehearsal. And it is basically just the activity of maintaining information until it can be moved into long-term memory. And this is most often in ways that we're just trying to learn singular words, done by just repeating something over and over. When we start talking more about rehearsal, you will see that this type of memory, or what oftentimes is referred to as rote memory, is actually not the best way of getting information into long-term memory in a way that it will endure and be easily accessible. Nonetheless, rehearsal in any of its forms is a key way in which memory is encoded into long-term memory. And while there are certain specific situations in which you can have a highly emotional situation and have something immediately encoded into long-term memory without any type of rehearsal whatsoever, they are those rare exceptions. You'll also see that in certain parts of neuroscience and cognitive psychology, there are theorists who talk about the concept of single trial learning or one-shot learning, which is this idea that you really only need one instance in order for information to get encoded into long-term memory, but it needs to be just right and not suffer from other types of situations around. And rehearsal is really just about going over and over until you get that sort of perfect trial in which you can encode something. Now, there's a lot of debate over this, but ultimately the consensus seems to largely be that you do require some degree of rehearsal for most types of information to be encoded into long-term memory. Now, another very important topic or concept in getting information into long-term memory is the amount of attention one devotes to those items in working memory that you're rehearsing and trying to get into long-term memory. For example, if you're juggling some balls while also watching a Netflix show while repeating a set of numbers to yourself over and over, chances are you will not be paying that much attention to those numbers that you're repeating over and over, and the likelihood is much less that you will encode those into long-term memory as compared to if you were just sitting with your eyes closed, not listening to anything or doing anything, as you focused on these numbers and repeated them over and over. The degree of attention you're devoting to these items will impact how well information is encoded into long-term memory. Another part of this also is the number of items that you have to remember. It is easier for us to encode information into long-term memory if, say, I only had 3 numbers as compared to 12 numbers. And this is because of differences in how attention is allocated. In the first one, I'm only attending to 3 different numbers, versus in the other, I have to attend to 12 different numbers. And this changes in the degree of attention I can devote to any single item, reducing, if my attention now is spread between more, the likelihood of each of those items to be encoded into long-term memory. Now, this lets us begin to take apart this idea of where the primacy effect comes from and how this is related strongly to long-term memory. So just a refresher, this term is used to define the increased rates of memory for items at the beginning of a list. And it is thought to be the primary result of our long-term memory systems and not our working memory system. Now, just also again, please remember that long-term memory is anything that is remembered that has spent at least a moment outside of your working memory. It can be things from 10 minutes ago, Technically, those things from 10 minutes ago that you haven't been thinking about continuously since then are now encoded in your long-term memory. Now, here we're looking at the performance rates of words recalled in two different conditions. In each of these conditions, they changed how much time each word was presented to the participants for. And the idea here is that when you're presented with words with greater time in between switching to the next one, you can devote an additional amount of intention to each of those words, be it one single word at a time or when you're rehearsing a list. For example, if the list was presented to you cat, dog, cactus, crocodile, if you had 5 seconds between each, you could be like, okay, cat, 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 cat until dog showed up. Then it's like cat, dog, cat, dog, cat, dog, cat, dog until cactus showed up. And then you can keep going. Versus if the list was presented to you like cat, dog, cactus, crocodile, then you barely have enough time to say cat twice before dog shows up. And then you probably only have enough time to say cat, dog once before cactus shows up. And so you just have much less attention that you can devote to each individual item when they're presented more quickly. So looking at this graph here, again, serial position of the words is on the x-axis and the percentage of correct recall is on the y-axis. And you see this pretty stereotypical shape where words at the beginning of a list are remembered best, along with words at the end. And then, of course, in the middle, they're not doing so well. But now here you can see that when there's a slow presentation of words, memory is consistently better at the beginning and throughout the whole middle section, which is probably all likely to be stored in long-term memory, as compared to when those words are presented in very fast sequence or progression. Now, what makes it, or what allows us then to say that this is specifically the process or function of long-term memory, is that as soon as you get to the end here, which is thought to be the effects of working memory systems, you see that the performance actually merges and they're equally good regardless of how quickly that information was presented to people. So, looking at the fact that we can have different conditions that modulate different seeming operations in the brain itself and how this has differential impacts on our memory performance is one of the greatest clues that leads us to believe that the working memory system and the long-term memory system, even though highly related, are technically two different systems that are operating within our brains.